Hello. Am I audible, sir? Hello, am I audible?
Yes, sir. Yes, sir. Hello.
Yes, sir.
Yeah, Nikhil, sir.
Yes.
Yeah, you're audible, sir.
Okay. Thank you.
Uh,
Nikhil sir,
Yes, sir.
who is Pankaj Wadil? Do you know? Is it from your DTPS?
There is one Pankaj Patil at DTPS, but I don't know if he is related to this module or not.
No, he just joined, but just we want to know ki you know him or what.
I know him, like there
Okay.
is one Pankaj Patil in DTPS, but I'm not sure because I haven't
Okay.
shared the link with him or anyone else.
Yeah. Okay.
So I'm not sure if it is same Pankaj Patil or anyone else.
Okay. I will check. Okay. Thank you, sir.
Yeah. Okay.
Good morning, all. I, Professor N.J. Panaskar, on behalf of Institute's Rajiv Gandhi Institute of Technology and Department of Mechanical Engineering, welcome you all to AICT AQIS sponsored online short-term training program on recent trends in energy management and audit. Our speaker of today's session is Mr. Nikhil Nirgude from Adani Power. He is presently working as Senior Manager Electrical Maintenance at Adani Dahanu Thermal Power Station. He has 9 years of experience at Adani Dahanu Thermal Power Station. His experience includes electrical machines maintenance and erection and commissioning of thermal power plants, solar PV, as well as concentrated solar power projects. I now request Mr. Nikhil Nirgude to take over and start with our discussion, sir.
Thank you, sir. And welcome everyone. Today we are going to talk about the energy conservation projects at DTVS. I think sir has very well introduced myself. My name is Nikhil Nirgude, and as you know from sir's introduction that I work at DTPS. So, sir, is it okay that we start the session or we are waiting for a few participants to come?
Start session, sir.
Okay, so before I start the presentation, I would like to request you all that we should keep this presentation very interactive. You can ask any questions you want, and we have 2 hours with us, so let's make full utilization of the time we have. Okay. Is the screen visible to everyone?
Yes, sir. Yes, sir.
Okay, so today we will begin with our first topic, which is energy conservation project at DTPS at Dahanu Thermal Power Station. Firstly, we will talk briefly why energy conservation is required. So the energy efficiency is important because if we consume more and more energy, then generation of this energy requires emission of greenhouse gases, which causes global warming. And we all are very well aware of the ill effects of global warming by now. So, due to shortage of peak power in the peak hours, there is a significant part of our country which is without power. Blackouts are very common in our country due to shortage of power in peak hours. So it is very necessary that we use energy efficiently and conserve energy so that everybody can get energy during the peak hours as well. During these peak hours, most of the energy comes from artificial lighting. As natural lighting is not available, we have to use artificial lighting. So there is a huge scope in lighting energy consumption to save energy and use it more efficiently. Like almost 18% of the total power used in our country is from lighting. And lastly, I would also like to tell you that once we save 1 watt of energy, it is equivalent to 2.5 watts of energy generated, because every watt of energy generated has some efficiency when it is generated, transmitted and distributed and finally utilized in our devices. So 1 watt of energy when we save at the generation level, it is equivalent to 2.5 watts of additional generation. So for energy conservation projects, it is very necessary to first monitor where the energy is used. Firstly, at the plant level, we have 100% monitoring of all the energy consumption at the operations levels. To identify energy deviation, we have various parameters like heat rate, which is the amount of kilocalories of coal consumed for per kWh of energy generated. Then we have APC, which is aux power consumption. Like for generating 500 megawatts at our plant, we have certain aux power consumption, which is the power consumed by the various auxiliaries in the plant. So we monitor closely this aux power consumption. Also, we monitor the fuel consumption. Like our primary fuel is coal in our plant. We also use oil, which is LDO, light diesel oil. So we monitor the fuel consumption also. Also, we monitor the process parameters, which are critical for energy consumption and energy conservation. Then we identify various energy losses in the system and we find the areas where we can improve the efficiency. Wherever there are deviations, like we have a standard benchmark set for energy consumption of equipment, and if there is a deviation, it is reported through FIR, which is first incidence report, notifications or work orders. This is our process. Then monitoring is necessary for providing right information in right time at right level. And there is data management system also, which collects data, compiles and keeps records for future references. Now the area under monitoring, it is very necessary that we cover entire plant area. So we are monitoring entire boiler, turbine, ash handling plant, coal handling plant, cooling water plant and FGD, which is flue gas desulfurization unit, which we are using in our plant. So this entire plant area is under monitoring. I guess everything is following very well. If there are any questions, you can ask. Okay. Since there are no questions till now, I'll keep proceeding. So we are using various monitoring facilities for this. We have HMI, which is human machine interface. It monitors the process parameters and controls them. Then we have X-Force and AIMS, which generates reports from these HMI data. Then we have online energy management system, which I'll explain you shortly later. Then we have D-Logbook, where we store the daily logs and events and local process parameters. And we also have an intranet website, which is our internal website where we share information of individual department and which is accessible to all employees of the plant as well as to visitors in case they want to see this information. Then for performance monitoring, like I said, we have heat rate, aux power, etc. performance monitoring. In heat rate, we monitor boiler and turbine losses. Then in aux power consumption, we monitor auxiliary power consumption of each auxiliary running in the plant by using online EMS, energy management system. Then we conduct energy audit as per CA guidelines. And for plant reliability, we keep tripping and event analysis and auxiliary running hours. Then before carrying out overhauling of our auxiliaries, we do a pre and post outage survey. So we know that what is the power consumption or energy consumption of that particular equipment before outage and after outage. So these all come under the performance monitoring of the equipments. Now I'll tell you about the major initiatives which are implemented in our plant to improve heat rate and aux power consumption. For example, heat rate is kilocalories per kWh for our plant, which is kilocalories is the amount of energy from the coal required to generate 1 kilowatt hour of electricity, kilowatt hour being the unit of electricity generation, and aux power consumption is the kilowatt consumption of the equipment. So ELAN system is consisting of a centralized database which gets data from data converters, which in turn gets data from energy meters. Each motor in the plant has each motor or even each individual feeder has a energy meter installed on it. These energy meters measure the data, which is the energy consumption of the equipment. They feed it to the data converters and the entire data is fed to a ELAN monitor, centralized monitor, which generates reports and signals, and this data is accessible to the key members of the plant. So this ELAN system provides a wide range of reports where we can monitor the daily consumption of any equipment in plant, hourly consumption, monthly consumption, as well as area wise, equipment wise, all reports are available in this system. So going forward to the next important project we have implemented in recent years. In 2017, we installed a 55 kilowatt solar photovoltaic unit on the rooftop of our administrative building. So as you can see, every year it is saving roughly 8,000 kWh of energy, and in last 4 years it has saved more than 2,53,000 kWh of energy. So if you see in 2017, the generation is slightly less because the project was commissioned in April or May of 2017. Therefore, first 3 to 4 months of generation was not available. So the generation is slightly lower in 2017, but we caught up in 18 and 19. Again, in 2020, you would see the generation is slightly lower because it does not include the generation of months November and December. It is only up to end of October. Right. Moving on, we have like in our plant we have a generator transformer, which is the major transformer which converts the power from generator to a higher voltage level. Now these transformers have cooling fans and pumps. The consumption of cooling pumps which was installed by the original equipment manufacturer was 4.5 kilowatt, as you can see here. Now we have installed new energy efficient pumps which were available in market. They consume only 2.8 kilowatts of power. There are 8 such pumps which run for 18 hours a day. They run based of the temperature of the transformer. They pick up and drop. So only 18 hours we can consider they run. And for 350 days I have considered, because 5 or 6 days the plant may be under outage. So considering this, if we calculate the kilowatt hour consumption, now if you may be aware or not, then the formula for calculation of kilowatt hours from kilowatt is, we take root 3, which is 1.73, 415 volts, 9.5 ampere is the current, and 0.85 is the power factor, and 1000 is for converting watt to kilowatt. And there are 8 such number of pumps running 18 hours a day for 350 days a year. So we get 2,92,000 kWh per annum. Now, if we replace this 4.5 kilowatt pump by 2.8 kilowatt, the consumption drastically reduced to 1,84,000 kWh, which gives us 1 lakh kWh or 1 lakh units of saving. kWh is just equivalent to what you call in domestic terms as units of energy, electricity. I hope everything till here is very clear to everyone.
Yes, sir.
Thank you. I'll like it if you give feedback or interact or ask questions in between. There is no problem with that. If there are no questions, then I'll move on. Okay. So now in our coal-based thermal power plants, we have an auxiliary called as electrostatic precipitator, which you may be aware of. So in this electrostatic precipitator, there are large number of heaters, shaft and support insulator heaters, we call them. These heaters have to cut in and cut off according. Yes, sorry. Okay. So these heaters cut in and cut off.
There is one question from.
Yeah, please. Please
from Sriram.
Yes.
His question is, do you have mathematical model of your plant to tell about what is expected?
Mathematical model of?
Plant.
Like our plant is a process plant, so we have a process and instrumentation diagram which includes the entire process movements and all, and we also have the logic diagrams of the plant. I really don't understand what you mean by mathematical models. Like, do you mean for energy consumption of equipments?
Actually, he is on YouTube streaming, sir. That's why. What exactly his question is?
Sorry. So basically, mathematical models are used in control systems, but here we are using a very complex system. So for energy conservation purpose, we have benchmarks for individual equipments, and these benchmarks are like for a certain auxiliary, we have a benchmark consumption, and if the consumption deviates above it, the energy management system will trigger a report or alarm, and from that we will get to know. So we will find out the cause and the energy consumption will be reduced. But for this, there is no auto control system. For this, we have to carry out some maintenance or some kind of modification in the system to reduce the consumption.
Sir, he is asking thermodynamic model, not mathematical.
Thermodynamic model, yes, or definitely every thermal power plant has a thermodynamic model. There is a curve for boiler efficiency and everything. Okay, I guess his doubt is clarified or not. Is this question regarding energy conservation, or it's just general question regarding power plant?
He's asking about the energy conservation, energy equations like.
Okay, so for energy conservation, we don't have a thermodynamic model. It is, we monitor the energy consumption or the heat rate or aux power consumption, and we control it using different modifications or maintenance practices. For plant process, we have a thermodynamic model or a mathematical model, but for energy conservation or reducing the energy consumption, we use maintenance practices as well as process control. Is it clear?
Yes, sir. Yes, sir.
So we'll proceed now. The major next major initiative for heat rate and aux power reduction is shaft modification of thermostat for heaters at ESP. So we have an electrostatic precipitator which has large number of hopper heaters, and these heaters are running for whenever there is a lower temperature, the heaters pick up which increase the hopper temperature, and again they have to cut off at higher temperature. Earlier, the thermostat was not located properly, which led to 24 hours running of these heaters. So we modified the location of the thermostat closer to the heater, which led to a modification in which the heaters are not running for 24 hours, but they are running for lesser hours, like for 12 hours, we can consider. So due to this, the consumption from heaters was reduced from 16,81,000 units to 8,40,000, like almost 50% consumption from the heaters is reduced. So we get more than 8 lakh units of energy saving from this project. And the next project or next maintenance practice you can say is that during every overall, we replace the HP turbine module in our plant. So like you can see for unit 1, the heat rate was 2010 kilocalories per kWh before overall. After overall, when we replace the HP turbine module, this heat rate changed from 2010 to 1980 kilocalories per kWh. Similarly, in second unit, it changed from 2006 to 1955. All these are in kilocalories per kWh. So this is a huge saving we are gaining by HP turbine module replacement during annual overhauling. Then as you may be aware, we have an air preheater in our plant. It's a coal-based thermal power plant. So we have an air preheater. This air preheater consists of baskets. The flue gas temperature is monitored at inlet and outlet of APH. If the flue gas temperature at outlet is higher, it means that the heat recovery from flue gases is poor. If the flue gas temperature at outlet is lower, it means that the PA and FD are gaining more heat from the flue gases. Heat exchange is very good. So APH is working very efficiently. So we monitor the flue gas temperature at APH outlet. So we carried out basket replacement during last overhauling. The temperature of flue gas at outlet of APH was 152 degree before this overhauling, and after the overhauling basket replacement, it changed to 130 degrees Celsius. So we are gaining 20 degrees Celsius temperature, which will reflect in boiler efficiency. Then in our plant, we also have a ball mill, which means that the mill is made up of a shell, which consists of a large number of balls, which are steel balls. And there are liners which lift these balls during rotation, and the balls collide against each other. During this process, the coal present inside the shell gets grinded. Now, if the the mill liners were earlier provided using manganese material liners by the OEM, later on we replaced them with high chrome material liners. This led to better grindability of the mill with lower power consumption. Like we were getting same power consumption, say a lower power consumption for same amount of coal output, grinded coal output from the mill. So here we have like 6 coal mills, mill 1, A, B, C, D, E, F, like likewise. You can see that 1472 kilowatt was the consumption of mill 1AB before this modification. It reduced to 1185 kilowatt. So that much power was saved just by replacing the mill liners. Likewise, you can see in all mills, it changed from roughly 1470 or 1400 to 1100 kW. And the next major initiative we used for reducing the aux power consumption was BFP cartridge replacement. So our boiler feed pump is an auxiliary which has a very high head and it lifts water from 0 meter to roughly boiler top, which is the drum level. So it has a very high head and its suction is from, it has a very low suction to delivers to a very high head. So the power consumption of this auxiliary is very high. It is the highest power consuming auxiliary in our plant. Like it roughly consumes 7,400 kilowatts of power and it is running 24 hours. So any small amount of power saving in this auxiliary will be huge saving for the auxiliary power consumption of the plant. So when we replace this cartridge, it reduces all the losses inside the pump, which are due to internal leakages and recirculation. So these losses are eliminated, and by replacing the cartridge, we get lower power consumption. Like for BFP 1A, we achieved a saving of 460 kilowatts. For BFP 2A, we achieved a saving of 650 kilowatt. Likewise, it varies with the cartridge replacement, and you can see from the graphs that from 7,404 kilowatt, we reduced it to 7,057 kilowatt, and same likewise for other BFP boiler feed pumps. Then next major energy saving or energy conserving initiative was like in every overall, we observe that there are some leakages in air ducts, which we monitor during running of the plant, and during the shutdown or overhauling, we attend these air ducts or flue gas duct leakages, which leads to reducing the loading of primary air fan, forced draft fan or induced draft fan. So loading of these fans is reduced and therefore there is saving in energy. So here you can see the ID fan loading was reduced from 1517 kilowatt to 1290 kilowatt. PA fan loading was reduced from 1914 kilowatt to 670 kilowatt, and FD fan loading was reduced from 283 to 260 kilowatt. So these were some of the major initiatives which we used for energy conservation. Most of these were based on maintenance, like we made some modifications or process alterations during the overhauling of the equipment, which led to lower energy consumption and better heat rate. Then there are other many small initiatives which we have installed, like these are turbine building rooftop ventilators. Earlier we used 3.6 kilowatt hour motor based ventilators. Now we are using self draft type ventilators, which saves 3.6 kilowatt hours of energy per ventilator. There are 14 such ventilators. So this is comparably very small gain compared to earlier projects, but still every gain is valuable to us. Then we have also installed solar water heaters at some buildings in our plant, like in guest houses and etc. Then we have installed solar street lighting at some areas in our plant. Like there are total 48 numbers of street lights having solar street lighting system, which saves 1056 watts of energy. Then we have also installed solar photovoltaic panels for water pumping water to the nursery near our training center. Now going towards the major power saving initiatives, we have variable frequency drives. People from electrical background will be very well versed with this. Some of you may not be very familiar, so I'm explaining the basics in a brief. I guess in tomorrow's lecture, our faculty will explain details of how these variable frequency drives work. I'll just explain the brief details. So speed of an auxiliary depends upon the frequency of the supply, electric supply, and number of poles, magnetic poles, north-south poles in the motor. So there may be 2 poles or 4 poles or 6 poles, and the frequency is standard in India, which is 50 hertz. So the speed is proportional to frequency and number of poles, and torque of the motor is proportional to voltage upon frequency. Higher the voltage, more torque. Lower the frequency, more will be the torque. So a variable frequency drive increases or decreases the frequency to increase or decrease the speed. That is the basic simple feature of this. And when you increase or decrease the frequency as the speed varies, let us see how we gain power benefits or energy benefits from this. Power is proportional to pressure and flow, as we know from the affinity law. Flow is proportional to speed and pressure is proportional to square of speed. Thus, power is proportional to cube of speeds. So very small variation in speed leads to very large savings in power. Suppose, for example, if you have an auxiliary which is running at 3000 RPM, but the required flow demands that the auxiliary should run only at 2900 RPM, the reduction of speed from 3000 to 2900 RPM, this small reduction of 100 RPM gives very large power savings as power is proportional to the cube of the speed. Along with power saving, VFDs also give other advantages. Major advantage being process control. Like for example, if you have a vessel and you want to control the level, then the VFD will control the flow by varying speed and the level of the vessel will be controlled. Then obvious other major benefit is energy saving. Third benefit is soft starting. Like whenever an induction motor starts, it draws a very high current during its starting. So this is not very good for the life of the motor as well as its starter. So if you use a variable frequency drive or VFD, it will start the motor from a lower current and gradually increase its speed and current. So the starting will be good and the damage to the motor will be eliminated. Same is written again that the module, which is the supply unit of the motor, it will damage to that will be eliminated. Then power factor. Power factor is a key parameter in electrical power consumption. Generally, induction motors which are lightly loaded have a very poor power factor. Therefore, their energy consumption is higher. So if you use a variable frequency drives, it brings the power factor near to unity. Power factor is from 0 to 1. 1 is a very good power factor. Normal induction motors have power factor near to 0.8 or 0.9. So variable frequency drive run motors have a good power factor. Therefore, its energy consumption is lesser. Then whenever an auxiliary is supposed to run at lower speed, but it is running at higher speed due to the motor limitations, then there will be some mechanical wear and tear. But if you use a VFD to reduce the speed, then this mechanical wear and tear will be eliminated. Also, best advantage of variable frequency drives is noise level reduction, especially in case of fan motors. So these are just some basic advantages of VFDs along with energy saving. I'll just explain how we can identify which motors we can install variable frequency drives on. Like if you go on installing variable frequency drives on every motor, then there will not be saving, rather there will be more initial cost and less benefit. So to identify which auxiliaries are suitable for VFD application, we carried out a survey. Here we can see there is a process pump or fan, and the flow of the pump or fan, whether it is a fluid or air, it is throttled using a valve. This is a motorized or manual or a valve or a damper, which is throttled up to 0 to 70%, and the output flow is controlled. It is not full, the full flow is not required by the process. Therefore, the flow is throttled. Now what happens is motor is taking full rated power and the flow given up to the wall is full, but the flow going after the wall is throttled. Therefore, the power is lost across this wall. So if we install a variable frequency drive on the motor, we keep this wall 100% open and the flow is controlled at the motor speed itself. So the motor speed is varied using VFD. Then the pump or fan flow will be controlled. Therefore, there is no power loss across the wall or damper, and the control flow is given by reducing the motor speed, which gives us variable speed as well as energy saving. I hope everything is clear till now. If you have any questions, you may ask. Otherwise, I'll proceed.
Yes, sir. There are few questions from the audience.
Yes.
Sadhna Purohit. Ma'am wants to know how to carry out flare design. That is her question.
Sorry, I'm not aware of this. What is flare design?
No. She has asked on YouTube streaming. So I'm just conveying her question to you. Like, uh,
How is it spelled? Flare?
flare, FLARE, flare design.
No, I'm not aware of this concept, flare design. Sorry.
Okay, thank you, sir. Sir, you
Any
can
other
continue, sir.
questions? No other
Uh,
questions?
no, sir. Till now, no questions, sir.
Okay, thank you.
Yeah,
So
you can
here we
continue,
have,
sir.
yeah, so here we have seen that a process without VFD has losses across a motorized valve or a damper. When the process is installed with VFD, by reducing the speed of the motor, we can eliminate these losses and save energy. So VFDs give a tremendous potential wherever there is a throttled valve or a damper. Only in those applications we can install VFDs. However, if the pump or flow is always running at a full flow and the process requires that full flow, then there is no point in installing VFD. There will not be any saving. So for identifying which applications we can install VFD in our plant, we carried out a survey. Total plant generation was 520 megawatt and the auxiliary power consumption for running this plant was 38 megawatt, which is roughly 8 to 10% of the plant generation. Then the ST motor consumption was 35. High voltage motor consumption was 35 megawatt and low voltage motor consumption is 1.75 megawatt. Miscellaneous consumption, which includes lighting, air conditioning, and other consumption, was only 0.5 megawatt. So here you can see miscellaneous consumption is 1%, LT motors is 5%, and ST or high voltage motors consumption is 94%. It may vary with every plant, but this is just what we found out in our plant. Then going further with our survey, we carried out a survey of individual HT motors. There are 42 HT motors. Out of these, 34 HT motors are continuous running and 8 motors are intermittent running. Now, if a motor is running intermittently for short periods, then there is no point in installing VFD or a variable frequency drive on that motor because the savings will not be significant. So we identified these 34 motors and continued our survey. Similarly, for LT motors, out of 460, 223 were continuous running and 237 were intermittent. So we focused on these 223 continuous running motors. Now we further break down these motors and carried the further breakdown of this data and found out the loading of each motor. So there were 11 motors which were loaded 80 to 85% of their rated design. Suppose the rated design of the motor is 100 kilowatt, it is only running at 80 kilowatts or 85 kilowatts. 11 such motors were identified. Only 3 motors, here you can see only 3 motors were running at their full capacity. Rest of all these motors are running at lower capacity than their design. So all of these have a very good benefit if VFD is installed on these motors, especially ones having loading lower than 80%. Similarly, we carried out the survey for LT motors. Here you can see a good 61 number of motors were properly designed and running at full load. The rest of all these motors were running at lower than their rated capacity. So they have a very good scope for VFD application. So finally, we found out that these 13 motors are very suitable for variable frequency drive applications, which included condensate extraction pump, coal mill sealer fans, and so on until elevators. So in the lecture about VFDs, my colleague will give you detail about each VFD and how it functions. I'll just explain to you how much energy is saved. This is our condensate extraction pump VFD. It is a high voltage motor, 6.6 kilovolt. And this is the variable frequency drive panel, which runs the motor at variable speed by varying the motor's frequency. So without the VFD, the consumption of motor was 590 kilowatt, or you can say 600 kilowatt. Once we installed the VFD, we reduced the motor speed up to 40%, sorry, 90 for 80%. So the kilowatt rating was reduced to 440 kilowatt. The energy saving due to this was 150 kilowatt. So if you apply this for 365 days per year, we get 12,60,000 units of saving. And if you apply the cost of the VFD, then the payback period came out to be 21 months. Within 21 months, this VFD has given back its cost, and now it is giving us additional benefits, additional savings. So this way you can see that how a single VFD can give such a large saving of 150 kilowatts continuously. Then in similar way, we installed a variable frequency drive for coal mill seal air fan. There are two seal air fans for coal mills, and one of them is running and one is standby at every instant. So we installed a common single VFD for both these applications. The motor consumption before VFD application was 122 kilowatt. With VFD, it consumes as less as 58 kilowatt. You can see it is almost less than 50% of loading. The net energy saving is 64 kilowatt. So if we had not installed VFD, the motor would have run at full 122 kilowatt and power would have been lost across the damper, which was throttled up to 50% almost. So with VFD, we open this damper 100% and throttle the speed of the motor rather than throttling the flow. So the motor gives lesser flow, which meets the process requirement. Now from this, we get energy saving of 6144 units for 350 days, which is 21,50,000 units. So you see, huge amount of energy savings can be gained by installing variable frequency drives for different motors. So this is a brief summary of energy savings which achieved from various VFDs and other projects in our plant. There are 4 number of sealer fans and the kilowatt rating, just now I explained. So they gave 24 million units. Unit is kWh, 24 million kWh of saving from sealer fan motors only. From condensate extraction pump, 10 million units. So if we go on adding solar plant and lighting project benefits, it comes out to be roughly 60 million units till date. This is data up to end of October 2020. 60 million units of energy is saved till now. And 668 kilowatt is the kilowatt saving, 60 million units of energy saving. Till here, I've explained you various energy saving projects in our plant, then variable frequency drive projects, how we identified the applications and how much benefits we have received from these variable frequency drives. The next part is about lighting systems, which is a major power consumption concern for not thermal industry, but residential industries as well as for government and distribution systems. Why? I would like to explain you shortly, because whenever lighting consumption is reduced or energy efficient lighting is used, it reduces your electricity bills and it reduces the incidences of power cuts, because power cuts come when the demand is higher than the supply. So if you use energy efficient lighting, everybody uses energy efficient lighting, then the incidences of power cuts will be lower. Then benefits to utility. Utility is any generating plant or distributing supplying company. The benefit to them is that decreased peak load. What happens is, generally throughout the day, the peak load is very low. And suddenly at evening, when natural lighting is not available, the peak demand is shoot up. So to meet this peak load, you have to keep the capacity of generation at a higher level. However, it is not utilized fully throughout the day. Only in peak hours it is increased. So if we all start using energy efficient lighting, this peak demand will decrease and there will be a uniform load throughout the system. And so if energy efficient lighting is used, there will be less power outages, which will be beneficial to power generation or distribution companies also, as their image will be improved due to lesser outages. Then benefits to government. Now, if the peak demand is reduced, then government will have to bring up lesser new power plants, because the peak demand is already met by existing power plants. So the investment required in power sector by the government is less. This will also improve the environment, as lesser number of power plants or lower capacity of power plant means lesser pollution. Then more power will be available for industries. Now, if you use more power in residential or lighting purposes, then power availability for the industries decreases. So if energy efficient lighting is used, then the rest of the power available can be diverted to industries for using. Now, there is a basic principle of energy conservation that you cannot save or you cannot control anything that you cannot measure. So first, to conserve anything or first to control anything, you should be able to measure it. So here we will see how lighting is measured. We all know how electricity is measured in kWh or kilowatt, or calorific value is measured in kilocalories, temperature in degrees Celsius. But light or the light intensity is measured. The light output of any lamp is measured in lumens. All lamps are rated in lumens, and the distribution of light or these lumens across a horizontal surface is called as illumination. The illumination across 1 square meter of an area is called as lux. One lumen in 1 square meter is called as lux. So a lux level is the standard for lighting. So every area will have a standard lux level requirement. For example, if you are in a living room, it will have a standard lux level of 100 to 150 required. So a lamp installed in a living room should be able to give a light output of 150 lumens per square meter, which is the lux level. Now luminous efficiency, or it is called as luminous efficacy, because the unit of power input is watts and the unit of output, which is light, is lumens. So it is also called as lumens per watt or luminous efficiency. It is the ratio of luminous flux by a lamp to the power consumed. Therefore, it is a efficiency of energy conversion from electricity to light. Now, another important parameter when it comes to lighting is color rendering index. The color rendering index is ability of a lighting source to distinguish different colors in its surrounding. So any light source which will be able to distinguish colors better will be a better light source. It is given defined as a scale from 0 to 100, which means a CRI or color rendering index of 100 means the light is very good for identifying different colors. If the scale is closer to 0 or lesser, then it means the color rendering is poor. So the light is not suitable for color distinguishing identification. So the importance of color rendering is whenever you are having a study room or a living room or a workshop where color identification is more important or a precise work is more important, then the CRI should be higher. However, for example, for outdoor lights, CRI may be lower, but efficiency is more important. For some cases, we have to find the balance between color rendering and efficiency. So there will always be, if CRI is higher, then the color rendering CRI is higher, then efficiency will be lower. And if efficiency is higher, then color rendering may be poor. So in most of the cases, we have to find the balance. And in some cases, we can compromise with CRI and go for more efficient lighting. In some cases, we can compromise with efficiency and go for best CRI available. A luminaire is a device which distributes and filters light uniformly using one or more lamps. So in layman's term, it is called as a fitting. So there is a lamp and there are lenses or reflectors, and there are other necessary equipments which are needed to run the lamp and for distributing the light uniformly. Together, all of these are called as luminaires. There is also control gear installed with a lighting. There is a ballast and igniter. Ballast is a current limiting device. Now, in case of discharge lamps like tube lights or sodium vapor lamps, they draw very high current during starting. So discharge lamp is having a negative resistance characteristic. Therefore, it drives very high current in starting. So these ballast will limit the current and voltage buildup, and it will provide only sufficient energy for the lamp to start. A igniter or commonly known as a starter, and the ballast is commonly known as the choke. So the starter is required for high intensity metal halide and sodium vapor lamps. It is basically a capacitor. Then incandescent lamp or the common lamps which have a filament inside them. We all know the filament, when electric current flows through the filament, it heats up and the heating or heating of the filament produces light. So in this case, lot of energy is wasted in the heating process and very small amount of energy is converted into actual light. So this lamp has limitations that it has short life and it is very inefficient. It was used in long earlier days, Now it is almost getting obsolete and getting replaced by newer generation technologies. Then there are gas discharge lamps. So the common tube lights or compact fluorescent lamps or CFLs come under this category. Also mercury vapor, sodium vapor, metal plate lamps.
आहे ना, आत्ताच गेले ते, बोल ना.
एक्झाम सेल मध्ये आज कोणी आलं नाहीत ना,
Yes, any
हा, हा.
questions?
तर ते एक मेल करायचं होतं एक्झाम सेल.
I guess
Hello.
somebody has some question.
Yes, sir. We have two questions from YouTube stream. Can I ask, sir?
Yes, yes, please.
Okay, sir. So first question is from Anant Iyengar, sir.
Okay.
Just a minute. Just a minute, sir. Okay, so sir Ananta Iyengar sir is asking what kind of backup in pumps or fans is provided in the power plant?
I guess he is asking about backup power sources. So in our plant, we have battery banks, which are a power backup for DC pumps. And we also have DG sets, which feed certain critical auxiliaries in the plant. Like these are not provided for all auxiliaries, but only for the critical auxiliaries, which are required to be run even in case of total power failure. So we have DG sets and battery banks for these backup sources.
Okay, sir. Thank you. There is one more question.
Yes, please.
Okay, so another question is from participant named Swapnil Mani. He's asking, what is the threshold between installing VFD on pumps and replacement with lower capacity and energy efficient pumps or motors?
This is a very good question. See, whenever we install a lower capacity pump, it is always better to install a lower capacity pump, but there is a limitation that you cannot vary it. It will always run at a lower capacity then. If you require variation in the process, like for in case of a thermal power plant, we have a condensate extraction pump. This will be a good example. The condensate extraction pump speed has to be varied according to the deaerator level or according to the plant load. If the plant is running at full load, the flow requirement will be more steam flow, and therefore the uh, feed water flow requirement will be higher. Therefore, condensate extraction pump will run at a higher speed. But at lower loads or whenever the deaerator is already running at a higher level, then the condensate extraction pump will have to run at lower speeds. So by installing VFD, we have a freedom that we can vary the speed anytime, and it will also vary in auto depending upon the command from the instrumentation or the DCS or from the PLC. But if you install a lower capacity pump, this freedom is not there. You can reduce the power consumption, but there is no freedom to vary the speed. So whenever you want a fine process control, it is always better to install VFDs. Whenever you have a fixed lower consumption throughout the life of the pump, it is always better to install a lower capacity motor. I hope this answers the question.
Yes, sir. Thank you so much, sir. Now you can please continue, sir.
Okay, so there are various gas discharge type of lamps. The light in this lamps does not directly come from heating, but instead there is a gas contained in the bulb. So in case of mercury vapor, it is mercury. In sodium vapor, it is sodium. So different types of gases are used. So what happens is when electric discharge occurs, these gas particles get fluorescence and they emit light outside the bulb. So basically these convert this type of lamps convert electricity into fluorescence and therefore emit light. Now in last few years we have come across a new technology which is compact fluorescent lamps. This is basically a gas discharge lamp or a fluorescent type of lamp. It has a gas filled mercury vapor gas inside it, and it has a magnetic or electronic ballast. So it is very similar to old type of lamps, only difference being it is more efficient and it is more compact. So uh, going next to the next detail, you can here see rating of each lamp in lumens per watt. LPW is lumens per watt. So So higher lumens per watt means better efficiency. So high pressure sodium vapor lamps provide lumens per watt from 63 to 140. Metal halide lamps provide from 65 to 110. Fluorescent, which is our common tube lights, they provide lumens per watt from 35 to 100. Now 35 to 100 lumens per watt means each watt of electricity consumed will provide 35 lumens to 100 lumens depending upon type of the tube light or the fluorescent lamp. Then twin tube or the compact fluorescent lamp will provide 50 to 70 lumens per watt. Mercury vapor lamp will provide from 30 to 60 lumens per watt. So here you can see different types of lamps and their efficiencies. Now we will see a small case study, like how once if we replace a normal incandescent lamp of 100 watt with 20 watt of CFL, then the saving is 480 kilowatt hours, considering that the lamp runs for 6,000 hours of its life. Here we subtracted 20 from 100, so we get 80 into 6,000 divided by 1,000, which is 480 kWh. So now here you may ask why I have considered 100 watt and 20 watt. So the reason is 100 watt of normal incandescent lamp gives same lumens of light which is given by a 20 watt of CFL or a compact fluorescent lamp. Similarly, 75 watt of old incandescent lamp gives same light output as 15 watts of CFL, and 60 watts of incandescent lamp gives 11 equal light output to 11 watt of CFL. So from these we can calculate the savings in energy in kWh for each lamp replacement. Then if we say that the electricity bill is rupees 3.5 per kWh, in today's time it is much higher. So you can say this saving will be much more. So from these we get 1,680 rupees of saving. Now the cost of changing lamp, here I'm not ignoring the cost of the lamp. So cost of changing the lamp is rupees 150. In case of normal GLS lamp, it is only 66. Now you'll ask why 66? It is just 10 rupees or 11 rupees. So I have considered 6,000 hours. In 6,000 hours is life for one CFL lamp, and 6,000 hours is roughly life for 6 GLS lamps, 1,000 hours being the life for one lamp. So in the 6,000 hours, we'll have to replace 10 incandescent lamps and only one CFL. So 150 rupees cost for one CFL, and cost for 6 incandescent lamp is 66. If you just look at the cost of the lamp, you will always say that incandescent lamps are better than CFLs because they cost only 70 rupees even if you replace them 6 or 7 times. But one CFL cost twice more than 6 normal lamps. But if you look at energy cost, it is much higher. So this is a very tricky part about electricity. The cost of the equipment is not much compared to the power consumed by the equipment in its life. If you look at more energy efficient motors, you will see similar pattern. The cost of the motor may be 10,000 to 15,000, and the energy consumed by that motor in its lifetime will be in lakhs. So never compromise in cost, initial cost for energy savings. So net savings you can see vary from 900 to 1600 rupees. This data I have got from Osram India Private Limited site. They also have stated that conversion of 1 million GLS, that is old incandescent lamps of 100 watt to CFLs of 20 watt, reduces 80 megawatt peak load. So the significance of this statement is that only if we replace 100 watt GLS lamps by 20 watt CFLs, 80 megawatt of plant does not need to operate. Just imagine how much cost is saved by that, and how much pollution is decreased, and how much investment is reduced. So by replacing 1 million 100 watt lamps by 20 watt lamps, you can reduce requirement of 80 megawatt generation. Now, until now, we have always heard about how CFLs are good, how much. Sorry, is there any question?
Sir, yes, sir. Sorry to disturb you, but there is one question from the participant, that if a compact fluorescent lamp are good at the cost savings, but as they have mercury, what about the environmental concerns?
Exactly, that is what I'm going to talk about in the next slide. That until last few years, we have always been praising CFLs and saying that how good they are, but now we know how many disadvantages they have. So the major disadvantage of CFL is that they are unsuitable for frequent on-off. If you frequently turn on and turn off a CFL, its life reduces drastically. they have high full light starting time. Like if you start a CFL, initially the light is dim and slowly it increases. So to get the full light output, it takes some time. Then dimming is not possible. Like you may have seen in some places, incandescent lamps came with dimmers. You can dim or increase the intensity of light, which is not possible with CFLs. Then they provide they actually generate a flickering light, which is not visible to our eyes because of persistence of vision. The flicker is very fast, but indeed they provide a flickering light which may be harmful to our eyes in very long term. Also, they have health hazards such as ultraviolet radiations. If you go for very branded compact fluorescent light, they will assure you that the ultraviolet radiations emitted are well within the given limits. But like any device, mobile or any electronic device, it does emit some level of ultraviolet radiations. Then it consists of mercury bulb, which is a very grave environmental hazard, and therefore disposal of CFLs is a big problem. Whenever a CFL is to be discarded, the mercury will be emitted to atmosphere or the land. Therefore, it is a very big problem how to dispose these CFL lamps, as they are hazardous to the environment. Then not in level of incandescent lamp, but CFLs also emit some heat. So this increases the temperature of the room, which will again increase loading on the cooling system, ventilation system, and it will also not be very desirable. And this heat is also again a loss to electric efficiency. Like some electricity is getting lost in converting to heat. Then CFL lamps are also very fragile. You may have noticed they have very low ruggedness, and they are very sensitive to temperature and humidity. So if there is wide range of temperature variation, very low temperatures or very high temperatures or humidity, the output of CFL varies. Also, they produce harmonics in electric system. Non-electrical people will find it difficult to understand, but I will explain it in simple ways. Like the electric waveform is sine wave or a sinusoidal wave, which is a desirable output wave for any electrical equipment. Whenever you install large number of CFLs, they produce harmonics, which is distortion from the sine wave. So whenever there is distortion from sine wave, it is harmful for other equipments in the electric network. Also, the CFL lamps produce a radio interference to radio devices. So in 21st centuries, as we have invented highly efficient and high output LEDs, we are switching from CFLs to LEDs. I hope this answers your question about the disadvantage of mercury bulb, which was very well pointed out. So the
Yes,
CFL
sir.
has large number of disadvantages. Therefore, it is time now that we should switch to LED lamps or light emitting diodes. So LED is slightly new technology. So I will explain how it basically works. Basically, a LED is a PN junction diode. There is a N-type material and a P-type material. A N-type material has excess number of electrons, and a P-type material has a lack of electrons. So whenever you combine them, it forms a barrier, and electrons start jumping across this barrier. At one point, they saturate, and there is a layer of barrier potential formed. So unless and until external energy is provided, electrons will not be able to jump this barrier. So if we provide electric energy, the electrons will start flowing again. And while flowing, these electrons will emit light. So to emit light, we have to use certain type of materials only. So we use aluminum, gallium, indium, phosphorus to emit red, orange, or yellow light, and indium, gallium, or nitrogen to emit green, blue, or white light. So different types of material will give you different colors of light. However, our main objective is to create white light. These LEDs can give different colors of light also, which will be good for decorative or indication purposes. But our main objective is to generate white light. So white light can be generated using two technologies. First one is mixed color white light. Here we have a red, green, and blue LED. Red LED is made using gallium and arsenic PN junction. Green LED is made using gallium and nitrogen PN junction. Blue using gallium and nitrogen with different doping. Doping is a process of imposing impurities in a diode. So these different LEDs provide different kind of lights. So if you have some basic knowledge of painting or color, if you mix red, green, and blue colors, the ultimate output will be white light. So this technology has very high cost of white light generation, but it has best efficiency. Then there is phosphor converted white light. Here what we do is we use blue light LED and we use a layer of phosphorus. This blue light excites the phosphorus to produce phosphorescence and generate white light. So this has very low cost and therefore until now it has a very high market share. So this phosphor converted white light is used in most of LEDs. Almost 90% LEDs, at least in present, use this phosphor converted white light. So LED lamps. Now each individual LED generates very small light output. Therefore, we have to use multiple LEDs so that they can produce sufficient amount of light output and they consume slightly higher power or input also. Then almost all LEDs have to have a optical system, which is they have a lens, and then the lens is used to provide a required beam angle. Beam angle is the angle in which the light disperses out of the lamp. Then there are different reflectors to distribute the light uniformly across the room. And there is an electronic driver. A driver is similar to a choke or ballast. Only difference is in tube lights we use copper ballast or a choke. Here we use an electronic ballast which consists of transistors. It controls the current flowing through the LED during starting condition, and they maintain a constant current in running condition so that the brightness is uniform and not a flickering light. I guess everything is clear till now. If anyone has any questions about the construction or basics of LED, then you can ask, otherwise I am proceeding. So the LEDs which are present in today's technology are suitable for dimming. You can dim the light from the LEDs. For this, pulse width modulation is used. Pulse width is, like I said, light is, electricity is a sine wave waveform. So the width of the pulses can be modulated, increased or decreased. Therefore, the voltage given to the LED will increase or decrease, and therefore light output will vary. And if you vary the pulse duration at higher frequencies, then the light output will vary. So this makes LEDs suitable for dimming, unlike CFLs. For example, if you have a 60 watt of incandescent lamp, it will be equivalent to roughly a 12 watt of compact fluorescent or CFL lamp, which is equivalent to 8 or 6 watts of LED lamp. So a 6 watt of LED will give same light output as a 60 watt incandescent lamp or 12 watt of CFL lamp. So you will see that the energy saving is huge compared to incandescent lamp and slightly lower compared to CFL lamps. Most popular type of size of LED lamps is 1 watt, 3 watt or 6 watt. However, in market we also have 10 watt, 30 watt up to 200 watts of LED lamps. The efficacy or the efficiency of conversion of electricity into light is claimed as 100 lumens per watt, and in future the manufacturers are aiming for 150 lumens per watt. So which means that for 1 watt of electricity consumption, 100 to 150 lumens of light will be emitted by the LED. Color rendering of LED is excellent. So you see that most of the limitations of incandescent or sodium vapor or CFL light are already eliminated by LEDs. The manufacturers which are most popular in market with LEDs are Philips, Osram, General Electrics, etc. Now we'll see why we should use LED lighting. First and most important advantage is low energy consumption for same light output. Then long life. Standard good manufacturer LED lamp should last for roughly 10 years. The efficiency of light conversion to electricity to light conversion is very high. It is suitable for dimming. It comes in small dimensions so that it can easily fit in your false ceilings or sockets. It has almost no heat generation. There is the LED lamps come with very good technology heat sinks which carry away all the heat and dissipate it properly. So there is very little heat generation. Then the light is directed using lenses. So you have a very uniform and a very good bright light coming from the LED lamps. They have a high color rendering index, which means the color identification in LED light will be much better than any other light. Then they are very much shock and vibration resistant. There is no ultraviolet radiation, and since there is no mercury, we can say it is environment friendly. Of course, there is a problem of disposal of plastic, but since the life of the lamp is higher, it means that there will be lower disposal or lower number of damaged fittings in long run. So we can say it is an environment friendly technology. Now we will compare the three technologies: incandescent lamps, CFLs and LEDs. Incandescent lamps are somewhat affected by frequent on-off. CFLs are highly affected by frequent on-off. If you frequently on-off a CFL, its life will drastically reduce, and LEDs have no effect by frequent on-off. Incandescent lamps instantly give almost full output on turning on. CFLs have some delay. LEDs also provide full light output on turning on. Durability wise, incandescent and CFL lamps are quite fragile. However, LEDs are very durable. Heat emitted by incandescent lamps is high, CFLs is medium, and LEDs is low. Sensitivity to temperature and humidity is negligible in incandescent lamp. In CFLs, it is very significant, and in LEDs it is slightly present. Then lumens wise we will compare. If you want 450 lumens, which is standard for a living room, then you will require a 40-watt incandescent bulb, or a 8 to 12-watt CFL, or a 4 to 5-watt LED light. So you can see, for instead of 40-watt incandescent lamp, you can install 12-watt CFL or just 4 watts of LED. So for 300, likewise, you can see from the chart, for different light outputs, we have different ratings for incandescent lamps, CFL lamps and LEDs. For 100 watts of incandescent lamp, you can replace it with 20 watts of LED. Now, like in initial case study, I took 6,000 hours because 6,000 hours was life of one CFL lamp and 6 incandescent lamps. Here I am taking 50,000 hours, which is life of one LED or 5 CFLs or 42 incandescent lamp. So incandescent lamp has a life of 1200 hours, CFL lamp 10,000 hours, and LED has 50,000 hours. We have 60 watts of incandescent lamp, 13 to 50 watts of CFL lamp, and 6 to 8 watts of LED. So the energy usage in its whole lifetime is, in 50,000 hours, is 3000 kWh, 700 kWh, kWh is units, or 300 kWh. Now, if you consider cost of electricity as 5 rupees, the cost for this energy consumption comes as 15,000 rupees. Cost for this CFL comes as 3,500 rupees, and LED comes as 1,500 rupees. The bulbs needed in 50,000 hours are 42, 5 and 1. If you reduce the cost of the bulbs 500, 400 and 200 rupees, the total cost for 50,000 hours comes as 15,000, 4,000 rupees and 1,700 rupees. So here you can easily see how much savings you can make by just replacing an incandescent lamp by LED. Your electricity bill, which was 15,000 rupees, will be reduced to 1,700 rupees only, even after including the cost of 200 rupees cost of the LED lamp. Now, if you compare, you will see that one LED costs 200 rupees, one incandescent costs just 10 rupees. You will easily say that why waste 200 rupees when you can use a lamp of 10 rupees only. But you see how much energy saving or financial saving you gain by just investing slightly more in initial ways. So I again emphasize this, that whenever you are using any electric device, do not consider the initial cost, consider its energy consumption throughout the life, then only make a decision which technology you should go for. So in 1800s we used candles, in 1900s we used incandescent lamps, in 2000 we switched to CFLs, and since 2008 we are gradually switching to LEDs. If you compare the electricity bills, you will find out that the cost of LED lighting for a room is very, very lower than candles. So there was a statement from Edison long ago. He had said that I will make electricity so cheap that only rich will afford to burn candles, which is very true today. Cost of burning a candle is much higher than using electric bulbs. So in our plant, we had installed these LED lights considering all these benefits and energy saving initiatives. These are different buildings in the plant: GCR, ESP, service building. Now the energy consumption was 18 watts of fluorescent lamp and 4 such lamps. Total wattage was 72. There are ballast installed in tube lights. So the effective consumption was 92. Total number of fittings was 100, running for 24 hours a day. Energy consumption was 173 kWh. Total consumption for year, multiplying it by 365 days, was 63,000 kWh. So for all these buildings, it came as 48 lakh kWh, kilowatt hour or units. 48 lakh units was the power consumption of all these buildings when we were using fluorescent lamps or tube lights. Now we replaced these tube lights with LED lamps. If you see, 18 watts of tube light was replaced with 9 watts of LED. Sorry. The power consumption was reduced from 63,000 kWh to 31,000, almost half. So for each building, if you keep on adding, the power consumption reduced from 48 lakh units to 15 lakh units. So that much saving we have gained. Almost half or 50% power is saved. More than 50% power is saved after installing LED lamps instead of CFL or tube lights. Here we have given the detailed calculation. 150 watt of HPSV fittings. We have measured, including the losses. The power consumed was 177 watt. Replacing it with LED, it came only 90 watts. Saving against each HPSV, which is high pressure sodium vapor lamp, the saving was 87 watts. So there are 60 street light fittings having sodium vapor lamps. The power saved was 5,220 watts. The per annum saving came out to be 22,863 kWh or units. Then the replacement cost was 1,66,000 rupees. So the per annum saving, financial saving was 1,07,000 rupees was our saving. So just by replacing 60 number of sodium vapor street lights by LED lamps, we saved 1 lakh rupees per annum. The expense of installing these, I also have to consider the expense of installing these new fittings. The cost of material was 2,43,000 and the installation or service cost was 50,000 rupees. So the total cost came roughly around 3 lakh rupees. So we have a per annum saving of 1 lakh rupees and we have a total cost of 3 lakh rupees. So our payback period roughly comes to 2.7 to 3 years. So you can see, by making such a huge investment of 3 lakh rupees, we get its payback only in 3 years, and in rest of the years, this 1 lakh rupees per annum will be our benefit. So here you can see how making costlier investments will give you higher benefits in future in terms of energy efficiency. I hope this calculation is clear to everyone and there are no doubts. So in colony area also we had 30 HPSV street light fittings, 150 watt each and 20 watt. They were replaced by 20 watt LED fittings. Total 28 numbers of 4 meter FRP poles and 58 LED fittings were installed on this. They were initially at 7.5 meter height for HPSV fitting. So we reduced the height of the pole also to 4 meter. This was done to ensure that the lumens or the light available on the ground level was unaffected. So we had to reduce the height of the pole from 7.5 to 4 meter and for replacing 150 watt 150 watt HPSV by 20 watt LED fittings. So again, similarly, we calculated losses and all, number of fittings, consumption, and finally we got a same average lux level. Actually, the lux level improved from 10 to 20. Now here it is street light, so the lux level is not 100 or 150 like your living room. The lux level for street light required is very lower because you don't have to carry any detailed activity or precise activities, just for general illumination. So the lux level, which was earlier 10, is now increased to 20. And the energy consumption is reduced from 23,000 to 5,500 only. So this is the huge amount of savings we got in street light modification in our colony area. This was how the earlier version of HPSV street light looked like, and this is the new LED street lighting we are using in our colony. It also looks aesthetically much better. So now in case of in case of fluorescent lamps, we need a ballast. Ballast is nothing but a choke. So these ballasts are made of copper, were made of copper in old days. They have a magnetic core and a coil wrapped around the magnetic core which opposes the change in current. With new technologies, we have got transistors with inductance or capacitance circuits in series, which also vary the frequency and regulate the current of the lamp. So now if we replace this copper ballast with electronic ballast, we will get many advantages. What are those advantages? I'll tell you briefly. These electronic ballast operate at higher frequencies, 28 to 32 kilohertz. They give energy savings up to 35%. As there is no magnetic core and copper coil, there is less heat dissipation. And again, the light will it lights up instantly. It gives full light output instantly. It improves the power factor. See, power factor is reduced because of the coil. So as we eliminate coil and you install a electronic driver circuit, the power factor is improved. They like in case of old chokes, you may have seen whenever the voltage is lower, the light intensity reduced drastically. However, these transistors control the lights in such a way that with slightly lower voltages also it gives similar light output. The weight of the fitting is reduced and life of the lamp is increased. Therefore, all of the benefits are much outweigh the initial cost. The initial cost of electronic ballast is comparably higher than the copper ballast, but their benefits are much more. So see, if you install a 10 to 12 watt of electromagnetic ballast, instead replace it with electronic ballast of 3 watt, there is a 9 watt of saving. And in case of CFLs, 5.5 watt of electromagnetic ballast if replaced by 2.5 watts of electronic ballast, 3 watts of energy saving. Compared to all other earlier projects, this saving is very small. But like I said, every watt of energy saved is important to us. So by installing such electronic ballast, we are gaining a lot of advantage and saving energy in our plant area. Also, just by replacing lamp, it is not enough. So we have installed solar lighting in many areas, just like mango garden in our plant. We have installed solar light. There are solar lanterns, solar street lights and home lights also. This will lead to not only to lead to energy conservation, but it will lead to promoting non-conventional and environmentally energy systems. Then now up till here now I've talked about replacing lamps, replacing ballast or using solar energy. But we can also conserve energy in existing system by proper switching of the lights. Most of the street lights or most of the lights in our area were earlier switched on manually. So to get additional savings and also for reliable operation, we used different types of auto switching systems. The benefit of this auto switching system is that not only energy is saved, but also the operation is reliable. For example, earlier we were dependent on some human or operator to switch on and switch off the lights. Now they will be switched on and switched off at required time in auto without any requirement for operator. So there are three types of different switching systems. First was the old one which we used earlier, which is electronic or electromechanical timers. They switched on at fixed timing. If you set at 6 a.m., the lights will switch off, and at 6 p.m. the light will switch on. Likewise, you can program it. Now we have installed a new technology which is photo sensors or light sensors. This sense the light in the ambient or natural conditions, and according to that the light are made on or off. The better advantage which we got from this was that sometimes in winter we have to switch on the lights earlier, or in summer we have to switch on lights later. So we don't have to go and change the timer setting. It will be taken care by this photo sensor or light sensor in auto. Also, other advantages in rainy days, whenever it is very cloudy, in afternoon hours also, if the light intensity falls below the set limit, the lights will be switched on in auto, which is also desirable feature of this photo sensor or light sensor. Then we haven't installed this latest technology, but we are soon progressing towards it. We can install motion or occupancy sensors. Like if there is some movement in area, only then the light will switch on, or if there is someone human present in the area, then only the lights will switch on. Otherwise, the light will switch off, which is done using motion and occupancy sensors. So these are all different technologies used for auto switching of lights. I guess I've cleared most of your doubts, and I've explained most of the energy conservation projects related mostly to electrical and slightly to the thermal power plant applications. So I guess that's all from my side. If you have any questions, you may ask.
Hello. Yes, sir. We have few questions.
Yes, ma'am. Please ask.
Sir, one question was, how do you conduct the pre and post outage survey, which you mentioned at the start?
Okay. So for conducting pre and post outage survey, we have different formats. So we distribute these formats within our team, which will be conducting the survey. So these formats include, like, one team will conduct the boiler audit or turbine audit, which must be covered in earlier topic. So they will find out what was the boiler or turbine efficiency before the outage, and after outage they will again conduct this audit and find out the efficiency. Some team will conduct the measurement of energy consumption of different drives, which is also available in EMS system, but we'll just collect that data and keep it available with us before outage, and then we'll again collect the data after outage. So in this way, we measure the power consumed in terms of heat rate or kilowatt hours electric power consumption of different auxiliaries before the outage and after outage, and then we compare that how much savings we have gained. Like in case of boiler feed pump, I have shown before cartridge replacement what was the power consumed by the boiler feed pump motor, and after cartridge replacement we measured what was the power consumed by the motor. Likewise, we do for every auxiliary or major auxiliary on which we are doing some alteration, modification, or maintenance activity.
Thank you, sir. There is another question.
Yeah.
The next question is about how do we avoid the installation failure or any other type of a damage while using a VFD with an existing motor?
Okay. So it is a common conception that variable frequency drive motors are frequently susceptible, or frequently insulation failures are noticed. So for these, many manufacturers are coming with new insulation processes such as VPI, vacuum pressure impregnation, etc., which are more suitable for variable frequency drives. So while if you are initially installing a new motor and you want to install VFD with it, you can ask the manufacturer for a VFD suitable motor. Otherwise, in our plant, we have run normal motors also with VFDs, and we have not noticed many insulation failures. It is not very common. Like condensate extraction pump, we are running variable frequency drive for more than 10 years, and not a single insulation failure was observed. And same was case with most of other applications. But still, if you are installing a new VFD driven motor, then you can ask the manufacturer for a VFD suitable motor.
Thank you, sir. Thank you for enlightening us with all the knowledge you have shared. Now I request Professor Gaikwad, sir, to propose vote of thanks.
Thank you, madam. It is my privilege to propose vote of thanks on this occasion as Professor Sambhaji Gaikwad on behalf of MCT's Rajiv Gandhi Institute of Technology, Department of Mechanical Engineering, and on behalf of Organizing Committee of AICTE AQIS, sponsored online one-week short-term training program on recent trends in energy management and audit. And my own behalf, extended a very hearty vote of thanks to Mr. Nikhil Nirgude for accepting our invitation as a resource person and sparing his valuable time with us. He has given good insight on the topic of energy conservation and discussed the different projects associated with respect to the energy conservation, efficiency, and how to save electricity bills. Thank you so much, sir.
Thank you, sir. It was my pleasure to share my experiences with you. And I would like to get any inputs from you or any suggestions for improving this presentation. Or I would also like to get any questions or queries from you, even if you wish to ask later on. I will
Yes,
be
sir.
available.
Yes. Afternoon session will start at 2:30 p.m. Please join all participants. Over to
Are
technical
there
team.
Yes, thank you, sir. Now I'm going to close this meeting.
Yeah, yeah.
Yes, sir. Thank you, sir. Yeah.
Thank you, sir.